Good morning. So, let us continue our course on rocket and spacecraft propulsion. For the last couple of lectures, we have been discussing the performance of ideal rockets. We have listed the assumptions that are required. Then we have defined certain parameters. One of those parameters were the thrust coefficient defined as F t upon A star P c naught, where F t is the thrust produced by the rocket, A star is the throat area for the converging diverging nozzle. Here we are considering the rocket to be like this, a combustion chamber and a converging diverging nozzle. So, this area is A star, the minimum area, throat area. The combustion chamber conditions are P c naught and T c naught, that is the stagnation pressure and stagnation temperature in the combustion chamber. So, we had defined the thrust coefficient like this. Then we have proved that the critical mass flow rate or the choked mass flow rate, and since the nozzle is going to be choked. So, this is the mass flow rate is equal to A star P c naught square root of gamma upon square root of R T c naught 2 upon gamma plus 1 to the power gamma plus 1 upon 2 gamma minus 1. So, this is the mass flow rate. As we can see here, the mass flow rate is a function of the throat area and the chamber conditions. Now, in order to increase the mass flow rate, since the throat area is constant, only way to increase the mass flow rate is by changing the chamber conditions. If we reduce the combustion chamber temperature, the mass flow rate is going to increase, or if we increase the combustion chamber pressure, the mass flow rate is going to increase. So, the possibility for increasing the mass flow rate, and we know that the mass flow rate will dictate the thrust, total thrust, because thrust is m dot u e plus the pressure term or m dot u equivalent. So, in order to increase the thrust, one way is to increase the mass flow rate. Now, we have also proved in the last class that the thrust coefficient can be made independent of every other parameter, but by the pressure, the pressure ratio and gamma. So, we have proved this in the last class. Gamma to the power gamma minus 1 minus P e upon P c naught to the power gamma minus 1 by gamma to the power half. This is the momentum thrust and the pressure thrust given as here. P e is the exit pressure at the exit of the nozzle, P a is the ambient pressure, A is the exit area, that is the area here, and therefore, we see that the thrust coefficient is function of gamma, the pressure ratio and the area ratio. However, we have shown before that area ratio is a function of Mach number, therefore, it is a function of pressure for the isentropic case, pressure ratio. Therefore, the area ratio is function of pressure ratio. So, we can eliminate this area ratio from here, and we can get it completely as a function of pressure ratio, and we had discussed that. So, what we have shown that C f is a function of the pressure ratio and gamma. Okay. Now, once the design is fixed, P e is fixed, then P e by P c naught is a function of area ratio. So, that becomes a fixed ratio. Then in order to change this, we have to change the pressure, but we have also what we have shown is that as we increase the pressure, the thrust coefficient is going to increase, but we have also shown that it cannot increase to infinity. There is a maximum limit when this ratio tends to 0, that is the exit pressure is very small compared to the stagnation pressure, we get the ultimate thrust coefficient. After this, we had defined the characteristic velocity as P c naught m star upon m dot. I have said in the previous class that the thrust coefficient essentially dictates the performance of the nozzle and the characteristic velocity dictates the performance of the combustion chamber. So, with this then we have proved that the total thrust is the product of thrust mass flow rate, thrust coefficient and characteristic velocity. Okay. And based on this we have also proved that the specific impulse will be product of Cm and C star. We have proved that in the last class. After that we had derived an expression for C star and we have shown that C star is equal to this. So, we have shown that in the last lecture and we had stopped here at the end of the last lecture. Now, we have the two expressions for specific thrust, the thrust coefficient and characteristic velocity. We see that the ISP is the product of these two. From our mission requirement from the very beginning, we have been saying that we want to maximize the ISP, so that our equivalent velocity will be higher. Now, the two parameters that dictate, if I look at this expression C star, then is primarily a function of T C naught and gamma. So, gamma is present in both and of course, the molecular weight. So, for a given fuel it is basically fixed. So, now again gamma for a given fuel or a given composition will be fixed, because the final composition of product will dictate what will be the value of gamma. So, the operating conditions that we have are essentially T C naught and P E by P C naught. Once again I have said that for the given area ratio, P E is fixed for a given P C naught. So, therefore, this can be replaced by P C naught. So, the two parameters that we have are the stagnation chamber pressure and stagnation chamber temperature. Now, coming to this expression, or rather this expression, first of all we can increase thrust by in three ways, looking from this equation. Either we increase the mass flow rate, or we increase the Cf, or we increase the C star. Okay. Let us say we want to increase the mass flow rate, and the parameters that we have are P C naught and T C naught. So, here is our expression for mass flow rate. We see that in order to increase mass flow rate, we have to either increase the stagnation pressure or decrease the stagnation temperature. If we increase the stagnation pressure, Cf is increasing. So, in this equation then both this will increase, and C star is not dependent on stagnation pressure to that extent. Okay. So, therefore, the thrust is going to increase if we are going to increase the stagnation pressure. Other way of increasing the mass flow rate is by reducing T C naught. As we reduce T C naught, as we can see from this expression, Cf is not that much affected, but if we reduce T C naught, our C star is going to reduce. So, characteristic velocity is going to reduce, and the net effect can be that the thrust may reduce. So, that also we do not want. Therefore, the better way of achieving a higher thrust is by increasing both P C naught and T C naught. However, there is a limit to P C naught. First of all, the structure puts a limit, because that will be the force exerted on the wall of the rocket by the gases. So, structures put a limit to that, and secondly, the temperature, if it is very high, there is a possibility of thermal defects on the wall, you need a lot of cooling, etc. And secondly, very high temperature will lead to dissociation of the gases, and when the gases start to dissociate, gamma is going to change, which is something we do not want, and dissociation actually is an endothermic reaction. So, it takes away some energy. So, therefore, the overall energy is going to reduce. Because of that, again the thrust produced will be less. I will discuss this dissociation effect again. So, bottom line is, although we can increase both P C naught and T C naught to get higher thrust, but there is a limit to it. That is why we cannot keep on increasing the thrust as much as we want. Okay. Now, this discussion where we have defined Cf and C star now will allow us to attempt design of rockets. So, that is what we are going to talk next. Simple rocket chamber, thrust chamber design, a nozzle design, and then I will solve a problem today on that. Let us now look at simple rocket thrust chamber. The rocket thrust chamber is the rocket motor and the nozzle, because that what produce the thrust. Okay. Let us consider that the inlet of the combustion chamber is 1, the exit of the combustion chamber and inlet of the nozzle is 2, the throat is given by star and the exit of the nozzle is E. These are the different stations. Okay. Let us also consider that the amount of flow going in is m dot in. This is the combination of both fuel and oxidizer, all the propellants. Let us also consider that because of chemical reaction, the heat liberated is QR. So, that is the Q that is added to this flow rate. Okay. And then this is the same flow that goes out, right. So, first of all, m dot in is equal to m dot out, because the mass flow must be conserved. If I draw the T s diagram for this process, T s temperature entropy diagram of this process, at the beginning of the thrust chamber at 1 we are here. Then what is happening here in the combustion chamber? In the combustion chamber, we considered the processor to be isobaric, because it was considered constant pressure process. That is what was proved by for isentropic process. So, we consider the process in the heat addition, process of heat addition, to be a constant pressure process or isobaric process. So, therefore, in the combustion chamber between 1 to 2, there is a constant pressure heat addition. So, if I plot it, it will be going to 2, and the pressure remains constant at P c naught. Okay. Now, because of the heat addition, there is an increase in temperature, right. So, the temperature here at 2 is now T c naught. So, this is the chamber temperature. Now, this rise in temperature depends on the amount of heat that is added, right. So, this will be equal to Q r upon C p, that can be proved from energy balance. Okay. Now, after the combustion chamber, in the nozzle there is an expansion. We are considering the expansion to be ideal. So, is isentropic. So, it is goes down vertically. So, this is our point E, exit. This is the pressure at the exit given by P e. We are not commenting about P e, but is isentropic. So, it is ideal expansion, let us say. In between somewhere it crosses the critical condition also, P star. So, from 2 to P star is isentropic, P star to E is isentropic. So, this is the cycle that the flow goes through from 1 to 2 to star to E. So, once again 1 to 2 is a constant pressure heat addition, and 2 to E is isentropic expansion. Okay. These are the two processes. Now, let us see what is happening. First of all, the energy is added in the combustion chamber. So, let us first do an energy balance for the combustion chamber. So, energy balance between 1 and 2. The total heat added is m dot, which is the mass flow rate, times Q r. This is the total heat that is added, and then this is a flowing process. So, from thermodynamics, you know, for the flowing process from first law of thermodynamics, since there is no work, the only work is the PDV work. Therefore, the heat added is equal to the change in enthalpy, stagnation enthalpy. So, the stagnation enthalpy change. Okay. Now, the stagnation enthalpy change is nothing but the stagnation enthalpy at 2 minus stagnation enthalpy at 1, that is the exit of the combustor minus the inlet of the combustor. So, this is equal to m dot H02 minus H01. Now, we have assumed the working fluid to a perfect gas for ideal rocket, which means it is thermally perfect, calorically perfect. So, therefore, H is equal to Cpt and we consider Cp to be constant. So, therefore, this can be written as m dot Cp T02 minus T01, and that is what we see here, that is what I have written here, Qr by Cp is equal to T02 minus T01. So, from this equation now I can derive the value, can estimate the value of T02. Okay. So, if I do that, from this equation I will get T02, which is the stagnation temperature at the exit of the combustor, which will be our T0C, Tc0 is equal to T01 plus Qr upon Cp. Okay. So, if the fuel and oxidizers are given, the propellants are specified, then for a particular propellant combination there is a particular heating value Qr. So, that is a known quantity. Then from the product Cp is also a known quantity. So, if these two are given, initial temperature is given, then we can estimate the final temperature. Now, in the nozzle the flow is isentropic, and we have proved that for an isentropic flow, H naught is constant. Therefore, H02 is equal to H0E, stagnation enthalpy remains constant. So, stagnation enthalpy at the inlet of the nozzle is equal to that at the exit of the nozzle, and H0E is equal to the static enthalpy at the exit plus the kinetic energy term u e square by 2. Therefore, we get u e square by 2 equal to Cp T02 minus Te. Okay. So, now in this equation Cp is known, T02 is known. If we can estimate Te, we can estimate the exit velocity ue. We are considering the nozzle to be isentropic. So, therefore, the process for the nozzle flow can be considered to be isentropic. So, we can use the isentropic relationship, and then for isentropic expansion in the nozzle, we get the exit velocity is equal to square root of 2 Cp T C naught 1 minus P e upon P c naught to the power gamma minus 1 by gamma. Here T c naught is equal to T02, as I have said, is the stagnation chamber combustion chamber stagnation temperature. Here what we have done is we have written this as Cp T02 1 minus Te upon T02, and then T02 we have put equal to Tc naught, Te by T naught 2 is replaced by Pe by Pc naught to the power gamma minus 1 by gamma. This is the isentropic relationship. So, since we are considering the expansion to be isentropic, we can write it like this. So, for the isentropic condition nozzle, this is the expression for the exit velocity. So, this is first time now we have an expression for the exit velocity ue, right. This you have also seen in gas turbines, the same expression. So, this will now give us the exit velocity at the exit of the nozzle. What we will do is we will simplify this little more. We will express it in terms of the known quantities which are given to us. So, in order to do that, what I will do is Tc naught I will replace by this equation. So, if I do that, I will get the exit velocity is equal to square root of 2 Cp T naught 2 equal to T naught 1 plus Q r upon C p 1 minus P e upon P c naught to the power gamma minus 1 by gamma. Okay. Now, we are doing an engineering estimate. So, as engineers we always make some approximations. Now, let us make some approximation. Let us look at this term T 01 plus Q r upon C p. T 01 is the incoming flow temperature. Typically, for gas turbines, when the flow enters the combustor, it has gone through the compressor. So, it is fairly hot, about 400-500 Kelvin temperature will be there. But for the rocket, it is coming directly from the supply. Usually, it is not hot. So, temperature is low. Okay. So, T 01 is typically low, and then combustion occurs, there is a rise in temperature. Temperature can increase by about 2000 up to 2000-3000 Kelvin, quite a bit of temperature rise. So, this delta C p, which is a temperature rise, is much larger than the incoming temperature. So, essentially we can write T 01 is much smaller than Q r upon C p. Now, if we make this assumption, then from this term we can neglect T 01, then u will be simplified to u e will be simplified to as a function of, it is approximation to Q r up. Now, once we make that assumption, we have a C p here and a C p here. So, this 2 will cancel off. So, it will be approximately 2 Q r and only this term. So, 1 minus P e upon P c naught to the power gamma minus 1 by gamma. Okay. Now, once again we are noticing something, we have eliminated the temperature again. What the exit velocity is a function of is the heating value. So, it is a propellant property, right. It is the heating value of the propellant and P e upon P c naught, but there is a catch to it. Here we are considering that the entire available chemical energy is being converted to the thermal energy or heat, right. So, we are assuming that the entire Q r is released, that is why we are eliminating T naught, because then T naught becomes a function, T c naught becomes function of the total heating value. In reality, it may not happen, there is something called combustion efficiency, all the heat energy may not be released. In that case, the temperature comes into picture, or what we do is we say that 90% energy is released. So, we multiply it with the combustion efficiency and then accordingly we can adjust to the requirement. Okay. Now, this is our expression for the exit velocity. Here we can also express the heating value as heating value per unit mole. If we do that, then molecular weight will also come into picture, like we had done earlier when we brought in the molecular weight in characteristic velocity. So, same thing we can do here also. So, if we consider Q r per mole, that is Q r bar, then my exit velocity will be equal to square root of 2 Q r bar by molecular weight 1 minus P e upon P c naught to the power gamma minus 1 by gamma. Here this Q r needs to be calculated using thermochemical analysis, which is part of the combustion analysis, as can be done, which we will do later. Okay. In the later part, when we go to the combustion, we will study how to estimate the value of Q r. So, at present this is our exit velocity. So, now we have the exit velocity estimated. So, for a given operation, now we can decide whether this whether a rocket is going to fulfill the mission or not. Okay. Now, to continue from here, what I will do now is next solve a problem to make these concepts more clearer. Essentially what I am going to do is I am going to design a rocket now. So, when you are talking about design, your boss will tell you that you have to produce certain amount of thrust, right. That is what the rocket designer needs. Then how do you design it? That is the question. So, let me solve a problem now. So, the question is that we are supposed to design a rocket, which means the thrust chamber as well as the rocket thrust chamber. So, rocket thrust chamber means the combustor and nozzle. Okay. So, we have to design a rocket thrust chamber. I will give you the conditions or the parameters under which we have to design. So, design of a simple rocket thrust chamber. Let us say that the propellants first of all is a very important parameter, because this m bar comes here, q bar comes here, qr bar, these are all propellant properties, gamma is also propellant property. So, first let me say that the propellants are given, it is nitric acid plus aniline, a very commonly used, both of them are very commonly used liquid propellants in rockets. So, nitric acid and aniline are the propellants. So, the chemical composition is okay. These are the propellants that are used. Now, it is also said that the mixture ratio, that is the ratio of nitric acid and aniline, is equal to 2.75. At present this informations we will not need, because that will go into the chemical composition and chemical analysis. Here now we are not doing the thermochemical analysis. So, we will not need this information, but for the completeness of the problem we are providing that. What we are going to need is the combustion chamber pressure, Pc naught. So, stagnation pressure in the combustion chamber is specified to be 300 psi A. I will give this problem in British units, okay, FPS units, because of the fact that this is essentially an American problem. Typically, this aniline nitric acid propellant are used by Americans. So, American work with this system of units. So, I will give this system of unit. You can convert this also to SI units. So, Pc naught is equal to 300 psi A. Atmospheric pressure, let us say this is the initial stage, the first stage. So, therefore, the atmospheric pressure is the sea level atmospheric pressure, which in absolute term is 14.7 psi A. So, that is the atmospheric pressure. Let us say that this rocket, this is the most important parameter, needs to produce 1000 pound thrust, that is the thrust this rocket needs to produce. We will give some more parameters. One is the constraint that the combustion chamber or the thrust chamber should have a cylindrical combustion chamber. So, the combustion chamber is cylindrical. Okay. Then the chemical analysis of this, as I have said that it will come from the chemical analysis. So, from the chemical analysis of the product we get certain parameters for this mixture ratio, for this propellant. So, the chemical analysis, the chemical results give that the Tc naught combustion chamber stagnation temperature is 4930 Fahrenheit, which is also equal to 5390 Rankine. Okay. Then the exhaust molecular weight of the exhaust or the burned product is given to be 25 pound per mole. Okay. Now, when you are designing this rocket, you have to produce certain ISP, you are designing it for that. So, the ISP is specified. Let us say the ISP is equal to 218 seconds, that is what you need. And again from the chemical analysis we get gamma equal to 1.22. So, for this now, these conditions we have to design a thrust chamber, that is the combustion chamber and the nozzle. We will first start with the nozzle. So, first let us look at the nozzle configuration. For the nozzle, what is the important parameter? It is the thrust coefficient. So, first for this case, let us estimate the thrust coefficient. We know that thrust coefficient is given as this plus this is the general expression for thrust coefficient. Now, here is a design problem, we do not know the area ratio. So, first thing is we start with an assumption that is an ideal expansion. So, let us assume ideal expansion. Now, with this assumption then P e is equal to P a, therefore, the pressure term in the thrust coefficient goes to 0. So, we are left only with the momentum term and exit pressure is equal to the ambient pressure. So, this P e is equal to P a. Now, in this equation the value of gamma is given, P e is equal to P a which is given, P c naught is given. So, I can directly calculate the thrust coefficient. So, if I do that, so therefore, P e is equal to P a, this implies the thrust coefficient after putting all the values will be equal to 1.41. Okay. Now, what does thrust coefficient give me? Why first we are estimating the thrust coefficient? Because we are supposed to design the rocket nozzle, right. So, design essentially means we have to estimate the areas. How do I estimate the area? I get this thrust coefficient. Now, let us look at the definition of thrust coefficient. Thrust coefficient is defined as the thrust by A star P c naught, right. That is how I have defined the thrust coefficient. Now, let us look at this equation. The thrust coefficient I have estimated already. The thrust is given, the stagnation pressure is given. So, only unknown in this equation is A star, the throat area. So, I can solve for the throat area from here as this. Now, the values are given. So, I can directly solve for this. This comes out to be equal to 2.36 square inch. Okay. So, 2.36 square inch is my throat area. Therefore, I can get d star, which is the throat diameter equal to 4 A star by pi. This is equal to 1.73 inches. So, that is my throat area for this rocket, 1.73 inches. Now, once we have this, and let us take the next step. So, first now we have designed the throat. Next, let us look at the exit area. Okay. So, let me draw the schematic here. What we have to design is this A star, we have to get this exit area A e, we have to get the length of this combustor L and the diameter of this combustor D. That is what we need to design. So, first of all, from here I get A star. Next step is to get the exit area A e. In order to get the exit area, we need to know the exit velocity. So, next let us calculate the exit velocity. How do we calculate the exit velocity? Let us again look at what has been given to us. What is given to us is the value of ISP, specific impulse. So, now we use the definition of equivalent velocity. which is equal to specific impulse times the acceleration due to gravity at sea level. Now, the equivalent velocity is ue plus Pe minus Pa upon Ae by m dot. But in this case we are considering ideal expansion. So, Pe is equal to Pa, therefore, this term is 0. So, the exit velocity is equal to nothing but ISP times Ge. ISP is given to me 218 second, Ge is the acceleration due to gravity, which is a known constant. So, I can get ue, this turns out to be equal to 7020 feet per second. Okay. Once I have this value, next we need to calculate the exit area. For the exit area, what I will do is I will use continuity equation. So, from continuity equation, exit density times exit area times exit velocity is m dot, total mass flow rate. Therefore, the exit area is m dot upon rho e ue, okay. And what is m dot from the definition of thrust for this case? From the definition of thrust, F equal to m dot ue. So, I can replace m dot as F upon ue, right. So, in this equation let me replace m dot by F upon ue. So, I get F upon rho e ue square. F value, the thrust is given, the exit velocity we have estimated. Now, we need to know the density. How do we get the density? For that, what I will do is I will multiply and divide by rho naught. Rho naught is density in the combustion chamber or stagnation density. So, this is something 1 by rho naught. Since we are considering the gases to be perfect gas, rho equal to P by RT, right. So, for perfect gas, rho equal to P by RT. So, rho naught equal to P C naught upon R T C naught. So, I can put it here, and rho e by rho naught by rho e can be given in terms of pressure ratio, because it is isentropic process. So, if I do that, this finally comes out to be equal to F upon u square. This is the value of R, universal gas constant divided by the molecular weight. R was coming there, T C naught by P C naught, P C naught by P A to the power 1 upon gamma. Here this ratio comes from the isentropic relationship relating rho naught by rho to P naught by P. Now, in this equation my thrust is known, exit velocity I have estimated, this is the universal gas constant which is a known value, this is the molecular weight which is given, this is given, this is given, this is given. So, everything here is given, I can just plug in the values and get the final area. This comes out to be equal to 8.6 square inch. Okay. So, now I have this area also, I have this area, I have this area. I can estimate the exit diameter, the exit diameter dE is equal to square root of 4 AE upon pi. So, this is 3.64 inches, about less than 4 inches. This is a small rocket we are designing. Okay. Now, we have these two parameters. So, now we have the nozzle configuration completely. One thing, the nozzle is essentially I am getting the throat area and the exit area. I would like to point out here that the shape of the nozzle still we are not talking about, because we have not discussed that. Later on we will come to the shape of the nozzle. Okay. At present we are considering this is a shaped nozzle, but we are not specifying what should be the shape. So, the nozzle part is done. Now, let us look at the combustion chamber next. So, for the combustion chamber, what we need to know, the velocity in combustion chamber. Typically, the velocity in the combustion chamber given by UC is much less than that in the nozzle, which is quite obvious, because combustion chamber conditions are almost stagnant, whereas nozzle has a high velocity flow. Now, this is something that we assume, this is a design parameter that we assume. So, let us typical values of UC is between about 200 to 400 feet per second, that is standard values of UC. UC lies between 200 to 400 feet per second, the combustion chamber velocity. For this problem, let us consider or choose that UC is 250 feet per second, it is a reasonable value, 250 feet per second velocity. Now, with this velocity, then first of all we use the continuity equation for the thrust combustion chamber. This is equal to rho c AC UC, which is equal to m dot. Once again, m dot can be replaced by u by u equivalent, f by u equivalent, as we have done here. So, if I come to this equation now, I can replace m dot by f by u equivalent. This UC will be equal to u equal to UC, this is rho c. So, everything here can be replaced, I can get an expression for the area of the combustion chamber. This you can write it as this is F only UC. See, this term F by U equivalent is my m dot. This term R by m T C naught, sorry, this will be P C naught by P C naught. This is my rho naught, that is the density in the combustion chamber, and this is U C, right. So, we have m dot by rho C U C, everything here is known. So, I can get the combustion chamber area. This is equal to 20.5 square inch. Therefore, the combustion chamber diameter is about 5 inches, okay. That is the combustion chamber diameter. So, once we have estimated the combustion chamber diameter, next we need the combustion chamber length. Now, length is something that depends on characteristic time and all, and the combustion instability parameters. At present, what I will do is, we will consider a length factor, which is typically given by the ratio of combustion chamber volume to the critical area. So, let us assume combustion chamber volume to S star. This is typically a given parameter which has been evolved through experiences. So, typical value of this is about 60. So, let us assume this value is 60. A star we have estimated. So, this gives us the combustion chamber volume to be 141.6 inch cube. So, roughly about 140 inch cube. Therefore, the length of the combustion chamber will be volume of the combustion chamber divided by the area of the combustion chamber. This is about 6.8 inches. So, if I draw the schematic now with the proper dimensions, first let me write down these dimensions. I will try to make it as much to the scale as possible. So, first let me write it that the length of the combustor I am getting is 6.8 inches, the diameter of the combustor is about 5 inches, the throat area sorry the throat diameter was about 2 point something, right. The throat diameter was equal to about 2.36 inch no 1.73 inches, and my exit diameter was 3.3 inches. These are the 4 parameters that we have designed now, estimated from the design. So, sorry 3.64, is it 3.64? no, sorry, this is 3.3 inches, not 3.64, that was a calculation mistake. So, if I draw it to the scale roughly about 5 inch, about 7 inch, then it goes down about 2 inches, about 3 inches. This is your rocket. With the propellant that we have, about this size rocket will produce 1000 pound of thrust with the given flow rates and everything. Okay. So, that is a small rocket which will produce the thrust. Actually, this kind of rocket can be designed in a laboratory and can be tested. Okay. So, that is one thing I wanted to show, that how we design a rocket. I would like to point out here once again that the nozzle we have considered only the throat area and the exit area. We have not considered the shape of the rocket. That will come later when we go into more detail of rockets, rocket nozzles. So, that is what we are going to take up next, the design of rocket nozzles. Before that, we will first define the nozzle the efficiency parameters, then we go to the design of rocket nozzles, and then we see how this rocket shape is designed. Once that is done, then we go back to the combustion chamber and we will do the thermochemical analysis to get the composition, to get the temperature, etc. I will discuss how those things are obtained. So, the next topic is continuation of our discussion on nozzles, and now we go into the shaped nozzles. So, I will stop here today. In the next lecture, I will start from there.